Hi everyone, welcome to Chapter 13. Today's Lecture 3 for ECO3411 will be on correlation. So it'll be kind of just the first half or first third of Chapter 13. The lecture on linear regression is going to last a little longer. So today we're going to look at the purpose of correlation analysis and then calculate a correlation coefficient, test and interpret the relationship. So we'll be going over these two learning objectives today. So correlation analysis. Correlation measures something very specific. It measures whether or not there is a linear relationship between two variables. We use a correlation coefficient to measure whether or not there is a relationship and how strong that relationship is between two variables. This would represent a positive correlation. That would be perfectly correlated, 1 to 1. They lie on that exact line, and that would be a positive slope. So that would be a perfect positive correlation. Likewise, we could have a perfectly negative correlation, and that would be a negative slope. There's several things that you need to know about a correlation coefficient. One thing is the correlation coefficient is we use a Pearson correlation coefficient, and it's measured as the lowercase r. That's the sample correlation coefficient. It shows the direction and the strength. So the direction, because it could be either positive or negative, and then the strength, because as it becomes closer to 1 or to -1, it is a stronger relationship. And we only measure it for continuous variables. We can't use categorical variables with correlation. So again, it ranges from -1 to +1. A value near 0, if r were to equal to 0, it would indicate a very low correlation, that there is not a very strong relationship. As x goes up, y goes up, or as x goes down, y goes up for that negative relationship. So if it were near 0, y goes up, x can do anything. We don't know. There's not really a relationship between them. All right. So there's my correlation coefficient. Let's talk a little bit more about it. So if we can kind of look, like let's just say we have a bunch of data. We've got hours studied and score. Hours studied and score in this relationship. So as hours go up, it tends to be that students' scores go up as well, right? There tends to be a strong positive relationship with these data. This is a negative relationship, but it's hard to tell what's going on. It's not as strongly linear. This is less strongly linear, so it would be a weaker, and it would be a negative correlation because it's downward sloping. And this would be no correlation. You just can't tell if there's an upward or a downward. This would be an r closer to 0. This would be an r closer to, say, -3. This would be an r close to +0.8, something of that nature. We are going to define the strength of relationships with correlation. We're going to say if the r, the correlation coefficient, is greater than 0.8, that's going to be a strong either positive or negative relationship. Why do we use the absolute value? What's the point of using absolute value? What does that mean anyway? Right. It means that we're going to drop the negative sign. So it could be a really strong correlation if your r were -0.9. The absolute value means we're just going to drop the negative sign or the positive sign. It's going to be kind of signless. It could be either negative or positive. Maybe that's a better way to say it. It could be either positive or negative, but as long as it's greater than in volume 0.8, it's going to be a strong relationship. It could be a weak relationship if your r is less than 0.3. If your r is, say, 0.21, then that would be classified as a weak correlation. And then in between 0.8 and 0.3, we're going to call that a moderate. These are guesstimates, but for interpreting the correlation coefficient, it's important that we have measures of like 0.8 or 0.3. Technically, it's more nebulous, but in this class, we're going to define it. So Minitab will calculate the correlation coefficient. The correlation coefficient will be the sum of x, any individual observation x minus x bar, y minus y bar, and then we're going to add them up across all observations. So if x and y are both big and x and y are both small, maybe that would be a stronger relationship. So one more time, depending upon the value of r, if the absolute value of r is greater than 0.8, we're going to call that a strong relationship. If the absolute value of r is between 0.8 and 0.3, there's a moderate correlation. And then less than 0.3, there's going to be a weak correlation. So here's an example. Let's do a correlation analysis using Minitab. In this case, we are going to grab these data, and I couldn't get it to copy directly from here into Minitab, so I copied these data into Excel and then from Excel into Minitab. And here we go. We've got these data in calls and sales right here. Does everybody see that? So these are the data, and we're going to do a correlation analysis to see if there's a relationship between the number of calls made and the number of copiers sold that month for a couple of offices of Copier Sales of America. So we have one observation for a salesman. They made 96 calls and their sales were 41,000 or whatever that number is. Likewise, for this guy, he made 72 calls and his sales were 39,000. Good. So we have this sample of individuals, and we're going to say, hey, for these guys, is there a relationship between the amount of calls and the sales? Is there a linear relationship? So in Minitab, what we're going to do, it's, again, super easy. So we're going to go stat, basic statistics, correlation. Stat, basic statistics, correlation. And then it's going to ask for some variables. And so I'm going to highlight that variable and select. Alternatively, we can highlight it and just click, go click, 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 and it'll go over. And so that now we can get a correlation between these two variables. We could add more and get correlation matrix among all those variables, right? But we just need two for now. So then we just say, okay, we're going to be, again, using the Pearson correlation, which is the default for Minitab. So here is my Pearson correlation. Pearson correlation coefficient is positive 0.86, and the p-value for the hypothesis test is 0. Again, why do we need a p-value? Ah, you're right. Oh my gosh, there is a hypothesis test in here somewhere, because this is a sample correlation coefficient. We only had a sample of 15. But we need to know, is there a correlation in the population as a whole? So statisticians have helped us out here. They allow us to do a hypothesis test to see how it is that the sample correlation coefficient is related to the true population correlation coefficient. So let's do a hypothesis test to see how the sample correlation coefficient relates to the true population. So this is what we just did. We put these data into Minitab, and then we ran stat, basic statistics, correlation. And then I chose calls and sales as the variables. And I said, okay. And this is my output, Pearson correlation and a p-value. So we can do a hypothesis test. Again, statisticians have a lot to do with this. Statisticians have a lot to say about what types of hypotheses we can do, and then the test statistics that we use for them. But every hypothesis has kind of the same format. We have an H0. This would be rho is equal to 0. There's no correlation between monthly sales and calls. We get this from a stat textbook, so it pretty much has to be the same. There is no correlation between X and Y, would be your H0. My HA, My alternative hypothesis is rho does not equal to 0. There is a correlation. I have a computed test statistic. My computed test statistic is from this formula. We actually have to put it in this formula. Minitab does not print out this test statistic for us, so we actually have to calculate it by hand. So in this case, my T computed, or my R, not my T computed, my R was 0.865. So this is a formula. This is a formula, R multiplied by the square root of n minus 2 divided by the square root of 1 minus r squared. So we have to actually put r from Minitab into this equation. We have to know that n minus 2 is 13 because n was 15. We only had a sample of 15 for this. And then 1 minus r squared. So we actually have to square 0.865 and then subtract that number from 1. When we do that, we get a T computed value of 6.2. But that is going to be something that we actually have to calculate. What a drag. It's kind of like we're back in the 1980s. All right. T table. In this case, the T table values, this may be one of the more confusing things if you haven't had it in a while, but you just have to memorize. We're going to split alpha, so we're going to go alpha divided by 2, so that would be T 0.025 with n minus 2 degrees of freedom. So my T table values will be equal to T, and then alpha. Do we have an alpha in here? Alpha divided by 2, and then n minus 2 degrees of freedom. Then we also have T 1 minus alpha over 2. And I would kind of like all of this down below, subscripted. I'd like to subscript this baby too. All right, so this is what we're going to be looking up. T table value is T alpha divided by 2, n minus 2 degrees of freedom. And that's the one that we're going to look up in Google. And then I'll tell you how to deal with that. You don't actually have to look this up in Google, though. So really what you have to know is that it's T025. It's half of alpha. Alpha is 0.05. And so half of alpha is T025 and then 13 degrees of freedom. This is basically what we're going to be looking up in Google if you actually want to, but you don't have to. And then T975 and 13. So the T table value with this hypothesis has two bounds, an upper bound and a lower bound. And we'll talk about that in a minute. But so we need both of these. And then my p-value, I look at my p-value from Minitab. And then what we do is from the p-value less than alpha, we reject. P-value greater than alpha, it's a do not reject. P-value less than alpha is a reject. There is a correlation between calls and sales. So this is from a stat textbook. This is information from Minitab that you use to calculate your T computed. This is from a stat textbook, the fact that we get this. This is from Minitab, and then this is a think for yourself. If p-value is greater than alpha, p-value is less than alpha. So this T table value, I guess I kind of did that before, alpha divided by 2, 0.025. Let's see where we got that from. But, okay, so you don't actually have to look this up. You do get credit for this portion. This is what we really get credit for putting that. But you may want to look it up. So let's figure out how we would look it up if we needed to. If we want to look up T025 and 13, that's what's available. We would look up T025 right here, and then 13 degrees of freedom. That would be 2.16. So that 2.16 is right here. This is T, 2.16. What you have to know is that if 2.5% of the distribution lies to the right, and this is 2.1 standard deviations away from 0, which is basically what this means. This is 2.16 standard deviations to the right. We need 975 because we're looking up 025 is here. 975 means 97.5% of the distribution lies to the right. This will be negative 2.16. So basically whatever you look up here in Google, just put a negative sign on it here. Whatever you look up here in Google, it's symmetric around 0, so just put a negative sign on it. All right, and then, so we would have 2.16, negative 2.16, and the reject region is as follows. If my T computed is, say, 6, then I would reject. If my T computed is 1, then it's a do not reject because it's in between a positive 2 and a negative 2. If my T computed lies in here, it's a do not reject. If my T computed lies here beyond this 2.16, it's a reject. So if your T computed is 4.5, you reject. If your T computed is negative 2.8, reject. If your T computed is positive or negative 1.5, do not reject. Make sense? So this is how we would use the T computed in the T table in order to arrive at your statistical conclusion of reject or do not reject. I think it's easier to not look all this stuff up and just use your p-value. And that's what I'm requiring in this course, because that's the way most statisticians do it, but it is nice to understand what a hypothesis test is. All right. In this case, after our hypothesis test, let's just look at a hypothesis test real quick, the kind of like the final hypothesis test. H0, there's no correlation between sales and calls. HA, rho not equal to 0. Rho is a true population parameter. That's the true population parameter. Just like we had X bar versus mu. Well, rho is like a mu for a true population correlation coefficient. HA is rho not equal to 0. There is a correlation. I'm going to calculate my T computed with information from Minitab. Here's my T table. And then I'm going to use my p-value because I'm not going to bother to look it up in Google unless I really have to, which you don't have to. So if p-value is less than alpha, you're going to reject. And if p-value is greater or equal to alpha, then it's a do not reject. There's not enough evidence to suggest HA. From here, we would do a summary. What does this Pearson correlation coefficient mean? What does it mean? Well, if my p-value is greater than alpha, my summary of the relationship is there's not enough evidence to suggest there's a correlation. So if my p-value is greater than alpha, what's my interpretation of that correlation coefficient? There's not one in the true population. There's not enough evidence to suggest there's one in the true population. And so that's what you're summarizing it as if your p-value is greater than alpha. On the other hand, if your p-value is less than alpha, and we know that there is a correlation, then I will further classify it as positive or negative, a weak, moderate, or strong. So with my summary, it is so important, you guys, look at your p-value. So in this case, if my p-value is greater than alpha, my rho might be 0. My correlation is there's not enough evidence to suggest that there's a correlation between calls and sales. On the other hand, if my p-value is less than alpha, then you would look at this R and say there is a strong positive correlation, which is the case, because I did have a p-value less than alpha and my R was 0.86. So that's pretty much all we're doing today. It's not that much. This is a summary. This is a correlation. Let's do some practice with the summary. We have Dow Jones and NASDAQ. These are two stock indexes. We got a Pearson correlation coefficient of positive 0.565 and a p-value of 0. What's the summary? Is there a correlation between Dow Jones and NASDAQ? Yes, there is a moderate positive correlation. My p-value is less than alpha. How about down here? Hours worked in student GPA. P-value of 0.19. There's not enough evidence to suggest that there's a correlation. I don't care if it says that in the sample it is negative 0.46. For the true population, we know we have to rely on statisticians for the true population, and that's why we say there's not enough evidence to suggest that there's a correlation. On the other hand, if my p-value is less than alpha, like here, you can say there's a weak negative correlation between interest rates and home prices. There's a weak negative correlation. Good? All right. Here are some multiple choice questions for you to practice with their answers right afterwards. Pretty good, huh? So those are very similar to what you can expect for the homework and stuff. Let's do a skills check. Skills check, skills check. This is what you're going to be doing kind of for the homework. So let's go through a problem that you'll be doing very similarly to what you can expect for your homework. So we have these data on final score and hours of study. This is a former math class, measured student test scores and hours of study. They would like you to run a correlation and interpret the Pearson correlation coefficient. So we want to take these data and we want to copy them into Minitab. Let's see if that'll work this time. Nah, it doesn't work straight. So what I do is I'm going to go here and go into Excel first, and then from Excel, copy and paste into Minitab. That seems to work better. So here we have final score and hours of study. So students' hours of study and then their final score. We want to test to see if there's a correlation and then interpret the correlation coefficient. So here we will go stat, basic statistics, correlation. Stat, basic statistics, correlation. And here we're going to have final score and hours of study because that's the one that we want. I went click, 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 click. And then I said, okay. And this is my result. I have a p-value of 0.001 and a correlation of positive correlation coefficient in the sample of a positive 0.743. Voila, that worked. Yay. See if you can do it. All right, so perform the hypothesis test. H naught, rho is equal to 0. There is no correlation between hours and score. HA, rho does not equal to 0 in the true population. There is a correlation between hours and score. My T computed, I'm going to assume that that's 0.7 just to ease the calculation burden. So it would be 0.7 multiplied by the square root of 13 divided by 1 minus 0.49. 1 minus 0.49 because 7 squared is 0.49. And if we do that calculation, we get a T computed of 3.6. My T table values are alpha divided by 2 and 13 degrees of freedom. 1 minus alpha divided by 2 and 13 degrees of freedom. My p-value is 0 or 0.001, so I will reject. There is a correlation between hours and score. And the summary would be there is a moderate positive correlation between hours and score. And next we'll jump into bivariate regression analysis. This is going to be a much longer topic. So although we only spent 30 minutes today, we may spend an hour and a half on that next lecture. So just work appropriately with that amount of time, because there's a lot more to learn with bivariate regression compared to correlation. But this does conclude our correlation lecture.